Okay, so unit one was on kinematics. Do you guys remember the definition of kinematics from one of the quizzes? Well, what is kinematics? Like things that are in motion, right? But it doesn't talk about the why they're in motion. It just talks about where they would be, right? I throw my pen across the room, right? We can figure out things like how long is it in the air for, how far will it travel, how fast will it hit when it falls, those sorts of things. This unit here on dynamic, it really more focuses on the why things move, what caused them to move. The key difference for this unit is we're going to talk about something called forces, which is today's topic, right? Why did this pen get thrown? I threw it. But why did it get thrown? Well, it's because I applied a force to it. Today's topic, we've got a couple of notes, but most of it's just reading stuff. So dynamics is therefore the branch of study which studies the effects of forces on motion, right? The key word being, I'm highlighting here, what force causes something to move. So kinematics studies the motion of objects, but we don't care in kinematics why it moves. Now we're going to talk about, well, what caused it to move? How did it get into motion? Maybe you'll hear some of these words in other places here. Classical mechanics, sometimes we call it Newtonian mechanics, describes like things that are macroscopic. Do you guys know the word macroscopic versus microscopic? Yeah, well, not necessarily really big, but microscopic means that like a human eye cannot see them. Macroscopic then would be anything that you'd be able to see, right? So if I were to throw something, can you see it? Yes, it's macroscopic. But can you see an electron moving? Okay, so that's microscopic. So if you can see it, and that can even include celestial bodies, we're eventually now going to talk about things like planets in motion, right? It can be super large, but I mean, we can figure out the physics behind how the moon goes around the Earth, or how the Earth goes around the sun, or how satellites move, that sort of stuff. So anyways, we're going to talk about things that are not microscopic. Anyways, long story short, though, we refer to these sorts of things as Newtonian. Basically, things that are of normal scale size. A little bit of history. I won't test you on this, but I think it's worth knowing. The two main people I want you to know their names of are Galileo and Newton. You've probably heard me tell the story about Galileo before. He had this crazy theory that everything was going to fall at the same speed. And people did not believe him whatsoever. So he did this experiment where he went to the top of I think it was Leaning Tower of Pisa, dropped two cannonballs of different sizes, and they both landed at the same time. Right? But at the time, people thought that heavier things fell faster. They don't fall faster, but they're going to fall with more force. If I were to drop a 1 pound something on my foot and drop a 100 pound something on my foot, hopefully you'd agree, the 100 pound something is going to hurt more, right? It's not falling faster, but it's going to have more force. So people back in the 1609 time frame, they weren't necessarily completely wrong, but they were using the wrong terminology. So, he also believed in what was called a heliocentric universe, and I've actually told this story to some people before as well. He realized correctly that the Earth actually goes around the sun, not the sun going around the Earth. You guys hopefully know this, right? The sun is actually the stationary body, more or less, and the Earth goes around it. But back in 1609, people actually thought that, no, the Earth is the center of the universe. The Catholic Church actually branded him a heretic and threw him in jail for the rest of his life. Sometimes I use this as a story to explain that you can be right, but if you cannot convince everybody else that you're right, if you don't show your work well enough to prove it, it's not worthwhile. Because he was totally correct. I think this is funny here. He was finally pardoned in 1992 by John Paul II. I just thought that was kind of funny. They finally said, we're going to not have him live his life and died being known as a criminal. So, it only took 300 years for them to finally agree. So that's Galileo. The other guy you should know a little bit about is Isaac Newton. There's a lot of people in the physics community who think this is just perfect symmetry. The year Galileo died, Newton was born. That's kind of cool, eh? And so basically one of those two, geniuses, I guess, of physics was alive for, a large part of the 17th century. So, He went to Cambridge. He was interested in studying these guys, Copernicus, Kepler, and Galileo. We'll talk about them as well. He's actually a founder of calculus, and we're going to talk about this slowly over the next few days. He published 3 laws of motion. So after today's set of notes, each of our next couple of classes, we're going to spend time talking about each of one of his 3 laws of motion. Okay, so let's start by talking about just some basic stuff of dynamics. The why of how things occur, that's forces. We want to know why things occur. So maybe you've heard this phrase before, a force is a push or a pull. Did I start the video? Why didn't you? Almost forgot. You guys have heard this phrase before, a force is a push or a pull? I could either push this chair, or I could pull it back, one of the two. But I want to read the second line here. It's more about the object's motion is changing. If something's undergoing a force, it has to have a change in velocity. If I'm pushing down on this table, am I actually doing any work? And the answer would be no. I'm not doing any work because it's not moving. And likewise, I'm really not applying any force, because a force has to require something to change its motion. If this table is currently sitting here, and I push down on it, is the table actually changing its motion? No. If something is in a current, regular old normal velocity, like if it's just going 100 kilometers an hour on the highway, really there's no force being applied to it. It's just traveling. If I speed up, the engine is applying a force to the tires, making us go faster. If I use the brakes, that would be a negative force, slowing us down. But if you're just traveling just a regular old speed, there's actually no force, because it has to be a change. Those are the key words here. You need to have some sort of acceleration. One of the things that we'll do then in this unit here is we'll draw what's called a free body diagram. This is the technical term for it. Essentially what we do is we draw a picture of whatever is the object that we care about, and we're going to talk about all the different forces that happen to be applying to it. So for example, I found this picture online. Here's a car. For example, the motor causes the car to travel one direction. If that makes sense. That's a force. It could cause it to speed up. But there's some drag pulling backwards. I don't actually know what RR stands for. I'm going to assume it has something to do with friction. But friction would cause you maybe to get slowed down backwards. Gravity's pulling you down. We don't actually cover lift force at any point, but there's a little bit of force that causes you to have lift, just kind of like how an airplane's able to take off, right? When the air is able to get underneath an object, it can actually pull it upwards. So we're going to draw a few of these today. It's actually not that hard to do. So let's do our first one. Let's draw a free body diagram for someone standing still. What was that? Is that the next slide you guys have?
Yeah.
Oh, okay. All right. So here's the first thing I need you guys to know. When it comes to drawing, if you want to draw an actual person, go for it. But my typical convention is I'm going to just draw a box. And that box represents an object. And because here's the thing, when we work in this unit here, sometimes we'll be talking about an airplane or a person or a car or whatever. And we don't care about drawing it out. You can if you want, okay? But I'm just going to draw a box. Okay, so this is a person standing still. What sort of forces are acting on the person standing still? Yeah, that's the big one, gravity. So we would draw a line pointing downwards, and usually we write something like this, F with a small g, indicating this is the force due to gravity. Now, if that were the only force acting on you, you would be traveling downwards. But you're not. There must be a force going in the opposite direction, preventing you from plummeting down into the Earth's core. What force is that? Take a guess. It's actually the force of the floor holding you up. Okay, let's talk about this for a sec. Let's say that I were to stand on the table, and the table can hold my weight. Would you agree that the table is, how do I want to phrase this? I am getting pulled down by gravity, but the table is capable of having to be held up. So it's almost like it's pushing back upwards on me. What happens if I start on a really flimsy table, and the table broke? Would the table actually have enough force to push back up on me according to gravity? Probably not then, right? So long as the surface on which you're standing is capable of supporting your weight in a way, then something is actually pushing back upwards. So long as it doesn't break, right? I go stand on that flimsy table there and it collapses. The free body diagram would be that gravity's pulling me down, but if there's no force pushing me back up, I will eventually fall until I hit the ground, at which point then the ground would push back up on me, preventing me from falling further. So we actually have a name for this. Whenever there's something that's pushing back upwards against gravity, we use N, and we call it the normal force. I have no idea why we chose the word normal, but that's the convention we have in physics. If something is pushing back against something, we call it a normal force. Does that make sense? So there's our free body diagram. If the force of gravity, let's just make up some numbers. You don't have to write this down, but let's say the force of gravity was 10 newtons, and my normal force was 10 newtons. Would you be moving? No. But what if the table, the really flimsy table I stand on, collapses, and it's really only capable of holding 5 newtons? What would happen? The table would break. I would fall. Does that make sense? But otherwise, if these two things were exactly equal to each other, then I'd be in a nice state where the forces are basically balanced. Think of like a tug of rope. That's actually the first slide I have on the entire set of notes way back here. If someone pulls this way and someone pulls this way, with equal forces, the rope doesn't move, right? Okay, so the next slide actually talks a bit about normal force, then just some stuff about it. So a normal force is a force perpendicular to a surface, and it's the force that keeps an object from falling. So what I didn't draw here on this last slide here was the surface. This is you standing on the ground, right? I guess I could draw it in the ground if I wanted. You guys know what perpendicular means? 90-degree angle, right? So if I wanted to, I could say there's like a 90-degree angle sitting right here. So here's the ground. The normal force is basically the ground pushing back up on you. Otherwise, you'd keep falling into the center of the earth. Net force is another set of words I need you to know. Basically, it's the sum of all your forces. If one person pushes this way, one person pushes this way, but they push equally, you won't move, right? But if someone ends up winning, I'll use my fingers, winning that fight, well, then you'll actually have a net force. So we may want to calculate that net force, but often it's zero. Often it actually ends up balancing each other out. This last thing here I'll talk about a little bit later here, but it actually is possible for an object to still be moving, even if the net force is zero. But I'd like to come back to that one in a bit. So, all right, last thing I threw on here. Often we'll use F for force, and there'll be all these little subscripts that we'll have. So like Fg could be a gravity force, Fa an applied force, Ff friction, T tension, N normal force. This is the one that's on your formula sheet. You'll probably see it as F net equals mass over acceleration. Is that on your formula sheet in that orientation? F net equals M over A. Okay, so they rearranged it. A equals M over F net. You guys see how it's going to be the same formula if you just change the order around though? So this is actually Newton's second law. We're going to talk about this on Monday, but one of the things we'll often want to work with is a net force. However, there's other formulas on your data sheet, one of which might be this. Ff equals a funny looking U times Fn. You guys see that one on there? All right, so Ff means this will be the force of friction. Fn means it'll be the normal force. So one of the things you guys will have to get used to is all the different types of forces we'll work with. Here's another picture of free body diagram. Here's a person pushing a box. So gravity's pulling it down. But keep in mind, if something does not counterbalance gravity, this box will just keep free falling to the center of the earth, right? So there must be a normal force pushing it back up, meaning the box is resting on a stable surface of the ground, right? If it was on a flimsy table, well, maybe it wouldn't, but it looks like it's stable. But here I'm putting some directions the other way here. If this person applies a force this direction here, which direction would friction go? Or wouldn't it go the opposite way? Doesn't friction basically oppose motion? I'm going to write that down here. Friction typically, I don't want to say always, but typically will oppose your motion. If, let's say I can't even move the box. Let's say the box is so heavy that I'm straining against it and I can't move it. Am I trying to apply a force? Sure, I totally am. Right? But friction is actually kind of pushing back at you, preventing you from pushing said object. So we can work in X and Y directions. Eventually, we'll start throwing in angles and doing stuff like that as well. Okay, so this actually isn't yet an example where we're going to do some math. I just want to illustrate something that's really common. So here's an example that we could solve. We're not going to. Let's say there's a car. The car has a weight of 10,000. Oh, I haven't mentioned this. Yeah, capital N. You guys know what that stands for? A Newton. Yeah, it's a Newton. That's the unit of force. A Newton is for force. So a car weighs 10,000 newtons down, and it's coasting on flat ground. It's coasting. Is there an applied force pushing it forward? And you can actually see that on this diagram right here. There is no arrow pushing it forward. It's experiencing a normal force of 10,000 newtons up. Does that make sense that these two numbers are the same? What if they weren't? What if the gravity force was more than the normal force? Then it would be falling somehow, right? By the way, here's a general rule. The normal force, though, should never be more than the gravitational force. Because if the normal force was bigger, then wouldn't it start to float? Right? So that's not going to make sense either. But typically, the up and down directions, they might actually be equal to each other. We're also going to have air resistance pulling us backwards and friction on the tires pulling us backwards. I don't actually have a question for us to solve, but do you guys see how I was able to kind of take this information and draw a diagram on it? Where there's a force acting up, a force acting down, and a couple of forces acting backwards. Okay, now let's actually make up a question. I know there's not one written here, but if I were to say, find the net force, you guys think you could figure that out? How much net force is acting on this thing? Idea? How much? 23. No. Because you're taking this and adding them together. Consider directions. If this is, say, positive and that is negative, wouldn't these two forces kind of balance and cancel each other? But wouldn't you agree that there's a couple of sets of forces pulling it backwards? So there's 2,500 newtons pulling it backwards. There's 500 newtons pulling it backwards. So your net force is going to be 3,000 newtons backwards. What we do need to, though, is work in both the X and Y directions. So you can see how kinematics, you know how when we calculated things in the up and down direction and in the side-to-side direction, that's not going away. Right? So we will still need to do things in X and Y. The good news is, though, in our physics class, we only do X and Y. We don't do Z. We don't do 3 dimensions, we just do 2. Okay, so let's try an actual example here then, what I kind of look for. There's 2 dogs. They're pulling a sled across a flat, snowy surface. Dog A pulls with 200 newtons. Dog B pulls with 150 newtons. There is some friction from the sled, and the driver also attempts to slow down the sled. Let's find its net force. So here's how I recommend you start. Draw a free body diagram. There's my sled. Honestly, draw a box. It's fine. We can draw a sled. Well, it looks like you're getting pulled forward, right? Dog A pulls you 200 newtons forward. Dog B also pulling you forward, but it's not quite as much, right? It's pulling you 150 newtons forward. Okay, the snow on the treads of your sled is pulling you backwards at 60 newtons. The driver himself tries to slow himself down by pulling backwards at 100 newtons. Are there any other forces? Gravity and normal, yeah. Often we're going to skip those because I don't actually know what the force of gravity is. But technically there is a gravity on this thing. But however much gravity there is, the normal force should be pushing up just as much. So even though I don't know those values, I should include them. I should just include them in the diagram, if that makes sense. We will work with those numbers slowly but surely over time. But to start with here, would you guys hopefully agree with me that going forward, you're going forward with 350 newtons total? But pulling you backwards is 160 newtons. So really there's not a formula to this. This is more of a, I hate to say common sense, right? So 350 minus 160, your net force is 190 newtons. Good. Forward. Yeah. Force is a vector. I should put that in a little note here. Force is a vector. Because we care about direction. Will this sled continue to move forward then? Yeah. Because the dogs are able to pull the friction that tries to slow it down, yeah, the sled will move forward. Does that make sense? Okay, well what if I throw some angles into it? We still handle this issue. So here you've got a car getting stuck in a snowdrift. In order to get out, one person is going to pull 75 newtons. And it's kind of pulling mostly east, but it's pulling 15 degrees upwards to the north. Then the other person is going to pull with 68 newtons, but they're kind of pulling in like a downward kind of direction. Right? So east, but 20 south. Friction is acting due west at 40 newtons. Let's figure out how much net force they have. You see how the change happens here now? It's not in one dimension, it's now in 2 dimensions. Right? So, the good news is there is a really easy way to solve this question, which I've been trying to prep you for in kinematics. You guys see what this is, a similar question type to? What's it similar to? Say it louder. The vector diagram, specifically cosine laws. That's what's going to happen here. You can almost think of it something like this here. Someone is trying to pull this way. Let's say just this guy pulled first. If you try to pull this way, that'd be good. And then in a way, if someone pulls this way, where would they actually travel? Well, they'd actually travel like that. It's almost like a cosine law. It's just one problem. It's not a triangle. Because it's more like this. Someone pulls this way at 75. Someone pulls back down this way at 68. And then someone pulls directly backwards at 40. This is where they'll end up at. Do you see how this is not quite a triangle anymore? Now, if it was a perfect triangle, you could probably use cosine law. But in this example here, I have to show you a different method of solving. So, good news is you'll actually like this in the future. Whenever you get a question that can just straight up be solved with a cosine law, you're going to be happy because it'll be like, oh, look, I can just plug it in the formula. But here, it's like there's a four-sided object where first it went here, then it went here, then it went here, and then that's the fifth side. I know I've kind of drawn this like a triangle. Maybe I should draw it a bit more. Give me a second, just to make sure it's really clear that this is not actually a triangle. So, travel this way for a little bit, travel this way for a little bit. Friction pulling you backwards. The net might be like that. You guys get what I'm saying here? So, if there were only two forces, we can use cosine law. So, new method then. So what we need to do is we need to consider things in the x direction And independently, we also have to consider the y direction. Figure how much force there happens to be in each of those. So I'm going to try to do work on two things simultaneously. What forces are acting in the x direction? Let's say this is x here, and that's y. Friction's pulling directly back, right? So I could almost say that I've got 40 newtons. I'm going to call it negative 40 newtons due to friction. That's one force. Okay, this guy's pulling at an angle though. Couldn't I make a triangle out of it and say that really there's a y component and an x component to this guy that's pulling at the upward angle? So that's what I'm going to try to calculate, is this top facing one here. How much forward is he pulling compared to how much upwards is he pulling? So we need to use our trigonometry. If I'm going to try to solve for fx right here, and I know the hypotenuse is 75, sine, cosine, or tan? Cosine. Right, because this will be the opposite. This will be the adjacent. That'll be the hypotenuse. So what I could do is I could say that the cosine of 15 degrees is equal to the adjacent. That's how much force I'm going to get in the x direction right here, over the hypotenuse. What's 75 times cosine of 15? Okay, so I'm going to make that positive 72.4 newtons. And I'm going to say that's due to, let's say, person 1. So person number 1, of that 75 newtons, a large portion of it is actually in the x dimension. That's good. But he's not the only person pulling, right? So to separate with another color here, I'll use green now. There's also somebody who's pulling with 68 newtons as well. It's 20 degrees for that person. Honestly, the math is the exact same though. You've got an fx, an fy, and the 68 is the hypotenuse. It's still cosine. You'll figure this out eventually. Cosine is always for the x dimension, and sine is always for the y dimension. Because really, what's going to happen here is you could say that the cosine of 20 is equal to the adjacent. The adjacent would be our x direction amount. The hypotenuse would be 68. So help me out again here. What's 68 times cosine of 20? 63.9. So then, again, I'm going to make that a positive 63.9 newtons. And that's due to person number 2.
Would you actually just write person number 2?
Honestly, you just need to notate this however works best for you. I'm trying to be very, very thorough here. Honestly, what I would do in the future is I would go fx1 and fx2, something like that for me, just to make sure I'm clear. But you probably picked up, this is where physics kind of goes, is you're just going to get a crap load of numbers you have to work with, right? And you just need to make sure you write them down, don't lose track of any decimal numbers. Highlighters work really well sometimes. But you need to develop really your own system for keeping track of values, because it's never going to go away, right? You'll always do this math to find that number, and this math to find that number, and this math to find that number, and you put those ones together, and then you combine it with that one. You know what I'm saying here? So find a way to notate it. But at the end of the day, hopefully this makes sense. Backwards was 40 newtons. Person 1 pulls forward, and person 2 pulls forward. So what's the total in the x direction? What's 72.4, blah, 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 plus 63.9, blah, 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 whatever that was, right? Minus 40. How much force is actually going in the x direction for it? 96.3? Okay. Again, I'll put dot 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 because you know the exact. So perfect. The car is moving forward. We're not done. Let's see why physics is. It's math, but it's a lot of math. Because now we need to deal with the y direction. Because of the way these guys are pulling, one guy's pulling up and one guy's pulling down. Hopefully the amount of y direction force is roughly going to be the same as each other. But can I guarantee that? Is it possible that this guy pulling upwards might pull the car so the car goes like a little bit uphill or a little bit downhill, one of the two? So we actually have to calculate that as well. So in the y direction, we don't have any friction, that's good. But we do need to calculate person 1 and person 2. The good news is this is now sine rather than cosine. So all you have to do is say that the sine of 15 degrees is equal to Fy1 over 75. I'll calculate how much upwards this guy is pulling. So what is 75 times the sine of 15? 19.4? Okay. And if it's okay, I'm going to make that a positive number, 19.4 newtons. Meaning that one guy is pulling upwards, essentially, northwards. What am I going to do for the downwards one, though, for value? Yeah, there's really no formula here, by the way, right? This is all about, you need to keep track of it logically in your own head. So I'll just write that up. That's due to person number 1 again. And then you want to do the exact same thing. You want to do the sine of 20 degrees Fy for the second person, and this is over 68. Anybody calculate that yet? 68 times the sine of 20? 15.3? 23.3. But I'm going to throw in here a negative sign, indicating that this person's going downwards, right? So, is the car going to go forward? Absolutely. But is it going to go forward in a completely straight line? No, not quite. What I would then say is I need to find the net in the up and down direction, and it looks like it's going to be just over 4 newtons downwards. What's 23.3 number minus the 19.4 number? Because really these are going in opposite directions, right? So the total in the y direction, it's got to be what, 4 newtons? It doesn't matter, we'll throw a negative on it, but yeah, what'd you get? 3.8, okay. And it really doesn't matter whether you make it positive or negative here. I would make it negative just so long as you recognize that negative is, we've chosen negative as the downward direction. Okay, last thing then. I'm going to redraw this diagram. So the car is definitely going forward, but it's going slightly south, down, which way we want that to be, right? So neither of these numbers is actually our net force. These numbers are this number on one side and this number on another side. Anyone can I guess what we're going to have to do? Say that louder. We have to do Pythagoras' theorem. Yeah. Because we have to calculate, kind of like in kinematics, you know how like I make you find the velocity of a thing as it hits? That's essentially what we're doing here. We have to figure out what's the actual resultant on this side right here. So we have to Pythagoras' theorem these numbers to try to find out what the resultant would happen to be. So again, you need to have some sort of way of saving all these values in your calculator. You can't round them ever. Anybody get a value? 96.4? Okay. Okay, so according to Pythagoras' theorem, this is 96.4. That's surprising, just because this one right here is also 96.3. But in a way, shouldn't it just be slightly more? If I were to draw this to scale, I didn't draw it to scale at all, right? But wouldn't 96 be like that? And wouldn't 4 be like that? So if I were to draw this line right here, wouldn't it just be slightly bigger than it was before? Just slightly. Do we get 3 sig digs? 2 sig digs. Okay. So 96 then? Is that what it would end up being? Okay, so our answer is 96 newtons. We're still not done. We need a direction. Are we going directly east? No. What I need for you guys to do now is calculate for me how much angle are we going cockeyed towards the south. Don't you love physics? It really is just a lot of math. Sorry. How do we calculate this angle here? Yeah, I would inverse tan myself. I would inverse tan the 3.8 over the 96.3. That'll work, right? If you do tan inverse of the opposite over the adjacent, that should give you this angle sitting right there. I can even write out most of it. I know that you're going mostly east, and you're going a little bit to the south. The question is just how much to the south are you actually getting pulled? It's probably like 1 or 2 degrees. 2.3? That makes sense? I don't mean to be the bearer of bad news, but that's a very, very typical, easy question. You'll actually, once we get further and further in the course, a question like that, you'll probably come to like that one because it's very straightforward. There's just a lot of numbers to deal with, right? And so you need to have your own organizational system to keep track of, well, what was force 1's y amount? What was force 1's x amount? What was force 2's x and y amounts? So it's very, it's time consuming, which stinks, because you have to basically be able to answer a question like this in like 4 or 5 minutes. So you got to be pretty quick at it too. That makes sense. Okay, let me do just one. Is it just the sine example? Yeah. Okay. Let me see if I can finish this in a few minutes here, and then we'll give you some time to work on your test. I think I can finish this in 5 minutes or so. Okay. One last example. So on this one here, can you guys picture the scenario? You've got a sign. There's a welcome sign sitting here, and it's being held by a rope right here and a rope right here. My goal is to calculate the tension on each rope. That makes sense. Like there's a rope right here that's kind of pulling it that way. If it wasn't for this rope right here, where would the sign be? Yeah, like straight down, right? Can you picture that? But they want the sign to get pulled in a little bit. So that's why there's the second rope. So I'm going to draw a free body diagram then. So where are the forces acting on this sign right here? One of them is acting kind of at an angle over here. So let me use some different notation this time. Let's call this the force of tension due to rope 1. It's also getting pulled this way due to the force of tension in rope 2. But there's another force. Which way would gravity pull this thing? Straight down. So straight down, I'm going to draw my last force, which is the force of gravity. If there were only 2 of these things, we probably could do the cosine law and just make a nice triangle out of it. But I don't think that's going to work very well on this one. So we kind of need to break this thing up again into the x and y dimensions. Hopefully you'd agree with me, though. This force of gravity is only in the y dimension, right? This force of tension is only in the x direction. This force of tension, though, right over here, the one at the angle, it actually happens to be something that I can break up into like 2 pieces. There's a certain amount of it that is the force of tension 1 in the x direction, and the certain amount that is the force of tension 1 in the y direction. You can almost break it up into 2 pieces. That makes sense? What's the only number I'm given? Force of gravity is 245 newtons. The only number I'm given. Sorry, you do get an angle, don't you? Let's deal with that angle in a second here. If this angle right here is, say, 55 degrees, is that actually inside the triangle we need? What would the number inside this triangle right here be? Yeah, 35. Why would it be 35? Because they add 90, right? Or what I could then say is, if this is another 90 right here, this one right here is also 55. So I guess I lied. You actually have 2 numbers, but in terms of a value that we can start working with, this 245 is really the only force value we have. Do we have any numbers force-wise on the triangle? Yeah, that's the key here. If this guy is pulling down at 245, it has to be balanced by something pulling back up, right? Isn't the only force pulling up this one right here? Wouldn't it have to also be 245? Wouldn't that logic make sense that this force right here has to be 245? Because if it wasn't, this sign would either be floating upwards in the air or it would be falling, right? So based on that, I'm going to now redraw my triangle a little bit here because it was getting a little ugly at the corner. You guys might not need to. This is the F tension 1 in Y. It must be 245. And I know that this angle right here is 55 and this one is 35. How do I find the tension in the rope itself then? I just use some trigonometry. Which angle do you want to work with? It doesn't actually matter which one we pick. 35 or 55? Sure, 35. Let's go with 35. Based on the 35 right here, this side here would be the adjacent. This side right here would be the hypotenuse. This side here would be the opposite then, right? So if I want to figure out how much actual tension was in the rope over here, I would say that cosine of 35 is equal to the adjacent, which was the 245, over the hypotenuse, which is the force of tension in rope 1. Just rearrange those guys. Take 245 and divide by the cosine of 35. That's how much tension was in this rope hanging off here at an angle. What'd you get? 299. So going back up to the diagram, this rope right here must have a tension of 299 newtons. Because we calculated the actual hypotenuse for the rope. So 245 of it is keeping it upwards, but it's more than 245 because it's at an angle. Because there must be some that's going this way here. However much this rope is pulling outwards, wouldn't this amount be equal to the amount that's going that way? However much this rope is swinging this guy out this way should be the amount of tension pulling it back this way. I don't take these two numbers and subtract them, right? How do I actually calculate this side right here? You gotta use trigonometry again, right? I would probably use, let's go back to this triangle here. You know how here we calculated the hypotenuse? Now let's calculate the opposite. So if that's adjacent and that's opposite, I'd use tan myself, but you can really use whichever one you want. I'd say the tan of 35 degrees would be the opposite. But this is really the force of tension rope number 1 in the x direction.
can just use Pythagorean theorem.
Or you can use Pythagorean theorem. Yeah, honestly, it doesn't matter. The only reason I prefer to use tan here is that this number here, 299.9, is a calculated value. So I'd have to make sure that I use every single digit on it. Whereas if I do it this way here, tan 35 equals opposite over adjacent. I don't have to worry about looking in my calculator for an old number, because I can literally just type in tan 35 times 245. But you're right, you can use Pythagoras' theorem. You could even use sine or cosine if you wanted to as well. But I gotta find the force of tension rope number 1 in the x direction. 171. Okay, so based on that, back up to my diagram, it looks like this guy is getting pulled backwards at 171 newtons. I'm going to throw a negative on there, not because it's really necessary, but just so that I can clearly see that the 171 is pulling it this way. It means that this rope right here must also be 171 newtons. Did you get something different? Who told me 171? Did you get 0.55?
Yeah.
Oh, okay, so it's 172?
Yeah.
Okay, sorry. It's fine. 172 then. Whatever. Okay, so actually that answers the question here. Determine the tension on each rope. This rope right here was 299 newtons, and this rope right here was 172 newtons. We could throw a direction on them. The only downside to this one here, I'm not going to do the direction on this example because I don't actually have a north, south, east, or west to kind of work with. But this one is definitely going directly towards the wall, and this one is going at its 55-degree angle. But there's our tension of 2 ropes. So, I was almost right on time here. Okay, so quick summary here. We're starting with a new unit on forces. It doesn't, I don't want to say it gets easier. It's just more of the same. If you're thinking that you have less calculations to do the more into the course we get, that's not true. I don't pull my punches when it comes to my expectations at first. So like the quiz, the test you guys are writing there, I don't know that it gets harder than that. But you need to be able to do multiple step calculations. Where in order to solve just a simple question, you're going to have numbers all over the place, right? You need to find your best way of keeping it organized. And that's going to be very typical. It doesn't get, how do I phrase this here? You know how you have all those formulas on your formula sheet? The really easy question is where you have to just use one formula off your formula sheet, plug some numbers in and get an answer. That doesn't really happen that often anymore. It'll happen once in a blue moon where it'll be like, here's a velocity, here's an acceleration, here's a time, find me a distance. But most of the time, you're going to have to put like multiple steps together to solve the question. So we'll just keep working on that. Okay, questions, comments, concerns, conundrums, all that stuff? Okay, you guys have just under half an hour. Sorry, I didn't quite time it well. Try to finish up your tests. When you're done, bring them to me. I'll mark them for you. And for any of you guys who are finished, before I start marking, do you want another minute just to look them over before I mark? Because you can have that if you want. I know you're finished. Who else is done? If you want, you can have another minute to look it over before I actually mark it. So it's up to you guys. Okay.